Hello and welcome to NASA's Jet Propulsion Laboratory in Pasadena, California. My name is Stephanie L. Smith. I'm part of the social media team here at JPL, and it's my pleasure to welcome you to the Cassini NASA Social, a series of conversations with scientists and engineers behind NASA's flagship mission to Saturn. Just hours from now, we expect the final transmissions from this intrepid orbiter. But before that, we've got conversations to have, and we've got a short video to roll for you. This will show you more of what's in store.
A lone explorer on a mission to reveal the grandeur of Saturn, its rings and moons. After 20 years in space, NASA's Cassini spacecraft is running out of fuel. And so, to protect moons of Saturn that could have conditions suitable for life, a spectacular end has been planned for this long-lived traveler from Earth.
5, 4, 3, 2, 1, and liftoff of the Cassini spacecraft on a million-mile trek to Saturn. We have cleared the tower. Bridge program is in. Full program is in.
In 2004, following a 7-year journey through the solar system, Cassini arrived at Saturn.
Around to the SOI burn attitude or pointing position and light up the rockets.
The spacecraft carried a passenger, the European Huygens probe, the first human-made object to land on a world in the distant outer solar system.
Huygens arrival on Saturn's moon Titan.
For over a decade, Cassini has shared the wonders of Saturn and its family of icy moons, taking us to astounding worlds where methane rivers run to a methane sea, where jets of ice and gas are blasting material into space from a liquid water ocean that might harbor the ingredients for life. And Saturn, a giant world ruled by raging storms and delicate harmonies of gravity. Now, Cassini has one last daring assignment. Cassini's grand finale is a brand new adventure. As it repeatedly braves this unexplored region, Cassini seeks new insights about the origins of the rings and the nature of the planet's interior, closer to Saturn than ever before. On the final orbit, Cassini will plunge into Saturn, fighting to keep its antenna pointed at Earth as it transmits its farewell. In the skies of Saturn, the journey ends, as Cassini becomes part of the planet itself.
And there won't be a dry eye in the house. So to give us a sense of how Cassini fits into NASA's exploration of the solar system, we have a very special guest all the way from Washington, D.C. So please welcome to the House Dr. Thomas Zurbuchen, Associate Administrator for the Science Mission Directorate at NASA headquarters. All right, Dr. Thomas Z.
Walking around here. I'm so excited to be here, and especially talking to the social media warriors here who are really helping us spread the word. So thanks for being here, and thanks for the work you do, talking about science, talking about the exploration stories that are out here, which are ultimately stories about humanity. That's really what this is about. And so Cassini is a really special mission for NASA. I want to just tell you a few numbers just so you get a feeling for it. At this moment in time, we have 106 missions that are either operating or in development. So that's the NASA portfolio. Of these, if I looked at the last 6-8 months or so, and I looked at the top stories that came out by audience participation, you know, like how many eyeballs, how many social media contacts, I looked at the top 20 stories or so. 17 of them come from the science mission director. There's other parts to NASA, as you know, but some of the just most amazing stories come from science. Out of the 17, and that's the point where I'm going, 8 of them came from Cassini. And it's stories that really moved people, and because of the depth of the type of questions that are being asked, and the questions that are really we relate to. Are we alone? Questions about where did we come from? Those are the very questions that are at the center of what planetary science is all about, especially in the outer solar system. So where are we? Where is Cassini in this? Well, you remember, of course, just a couple of weeks ago, we celebrated the 40th anniversary of another couple missions, which are Voyager. They were really the first ones to zip by these worlds, giving us a glint of what's to come. And 2 of these worlds was visited again. One of them, Jupiter, multiple times over. Galileo, Juno is in orbit right now. And this one we visited with Cassini. So you see, we flew by with Voyager. We visited, went into orbit with Cassini and spent, 13 years or so in orbit. So what's next? Well, what we're learning and what you see from other planets is what we really want to do is peel back the kind of cloak of ignorance and really look at the next type of questions. And what will happen here is the questions that are really at the center of what excites us, and the science community that's coming here requires as a next type of step, perhaps landing, perhaps a much better, much higher resolution type of investigation than what we have done here. So think of Cassini really as a major milestone on a journey of exploration where some of the best stuff is yet to come. So for me, this is an ending. But like every ending, it's really a beginning. It's the beginning of dreaming beyond. It's the beginning of exploring beyond, and really for us to be excited and motivated to put together what are the next investigations, the next missions that will come both of NASA, often with contributions from others or other agencies. So for me, that's what Cassini means. And so what I'm going to do is just open it up for questions to see whether you want to shoot some rapid questions and see whether there's anything you wanted to chat about that I missed. Yes?
You talked about questions that are to come.
Oh, go ahead and wait for the microphone to come to you.
You talked about questions that are to come with the next mission. What are some questions that you would like to have answered?
See, the question that relates to life, it's a question that, frankly, I don't think many people expected we would be asking in the context of the outer solar system. See, what happens, sometimes people talk about research like peeling the onion. And I said, that's really wrong, because see, when you peel the onion, it kind of the next layer looks a little bit like the layer before. It's just farther in. Well, the way the nature research kind of works is like you peel back an onion, what comes underneath is an apple. You peel back an apple, what comes underneath is a monkey. So it's basically what happens is the type of questions that we unravel are questions that we don't expect at the beginning. So right now, if I had to guess, the questions that we want to look at are questions both about just the physics and the environment, the history of the solar system, but very much life. But once we start looking at that, it's not one question, see, it's a whole way of investigating that. If you want to look at that, we're peeling it away, a new question will arise in a way that will surprise us tremendously, just like we were surprised here.
Well, Dr. Thomas Z is very active on Twitter. We have a jam-packed rundown today and lots of folks to get to. So if you have other questions for the good doctor, you can find him at @Dr_Thomas Z. So thank you, Dr. Thomas Z.
Thanks so much. Good luck.
All right. So this is a conversation, not a presentation. And we want you to be part of it, both the people who are here in the house at the NASA Social and all of you watching at home or streaming this live online. So go ahead and either Join the conversation by raising your hand in the house or tagging your questions on social media, hashtag AskNASA. Our first panel up today is our science panel. And every mission starts with science. Science is the pole star that guides us. It's with us every step of the way. Science dictates the instrument payload on a spacecraft and the maneuvers that it takes during the mission. So today, we've got some special guests, and let's welcome them to the stage. We've got Linda Spilker, the Cassini project scientist. Come on up, guys. Join our little fireside chat here. Jonathan Lunine, an interdisciplinary Titan scientist from Cornell. Connor Nixon, the Sears Instrument Deputy Principal Investigator. And Morgan Cable, Assistant Project Science Systems Engineer. Now, that's quite a mouthful, and I want them to tell you in words that non-experts all understand what it is that those things mean. I've asked them all to prepare and think about a few anecdotes from the mission and images that were very, very special to them. But in the interest of getting to as many of your questions as possible, we're just going to start by having them say what it is that they do on the mission, one after the other, and then we'll go into questions. And if in the answer of one of those questions you want to call for those slides, then we'll pull them up. Okay, so Linda?
I'm the Cassini project scientist, and I've been very fortunate to work on Cassini for almost 30 years. And if you think about that, that's the time it takes Saturn to circle the sun once. So I worked on Cassini an entire Saturn year. And a story that I tell is that my oldest daughter, Jennifer, had just started kindergarten when I started working on Cassini. And now she's married, and she has a daughter of her own. So these long projects can actually be multi-generational, and it's wonderful to work with this incredible team of international scientists, and it's going to really be sad to say goodbye.
Well, I'm Jonathan Lunine, and the term interdisciplinary scientist means that I have responsibility on the mission for a particular science area. In my case, Titan's surface, what is it made of? How does it interact with the atmosphere? How does it put gases in the atmosphere and the gases come to the surface? And my role has been during development to make sure that that science would get done, and then during the mission to help with deciding which observations should be done on which passes of Titan. And thanks to the wonderful discoveries at Enceladus, I've had a chance to work on Enceladus as well. So it's been a remarkable mission for me. The breadth of science that goes on every day has just been extraordinary.
So I'm Connor Nixon. I work at NASA Goddard Space Flight Center, which provided the composite infrared spectrometer that's on Cassini, one of the core optical remote sensing instruments. I work now as the deputy principal investigator of that instrument. And in fact, working on Cassini has been my entire career. So I started out in graduate school before the launch of Cassini, helping to build the Sears instrument. And then I continued on all the way through the launch, the Jupiter encounter, which was a very exciting tryout period for Cassini, all the way through to getting in orbit, and then actually doing the science with Sears, which has given us a lot of remarkable discoveries, including the infrared signatures on Enceladus' South Pole and the discovery of new molecules in Titan's atmosphere. So very exciting to be working on this mission.
Hi, I'm Morgan Cable, and I haven't been working on Cassini's for 30 years, but a relatively recent addition. But I think that's one of the wonderful things about Cassini is that we're able to bring in people closer to the beginning of our careers, and we can be mentored by some of these amazing scientists and engineers. My role has been to support Linda and the Deputy Project Scientist as a Project Science Systems Engineer, and basically help the scientists and the engineers communicate across the Cassini mission, because oftentimes they'll speak in different languages. But it's been so much fun learning and watching this amazing mission grow, and I can't wait to see what's next. This is just one chapter of Cassini. This is a start of a new chapter, and I'm excited to see what new discoveries we'll find with the data analysis to come.
Fantastic. Okay, with that, let's start the conversation. Do we have questions for our science panel? Just wait for the microphone to come to you.
Hi, thank you. Technology changes a lot since Cassini was launched in '97. Are there tools or instruments that you wish Cassini had on it that are available today? And I guess in that sense, that if you're able to do a return trip to investigate the moons, what would you most want to put on it to get more information?
Well, I'll start. No, I don't wish that any instruments we have today were on Cassini, because then we'd end up in this continuous vicious circle of time travel where we're waiting for the next terrific instrument. The thing about the Cassini payload is that it was remarkably broad and deep. And yes, today those instruments are obsolete, but what they were able to do, which I think is one of the most astounding things about Cassini, is that they could actually follow up on their own discoveries. So let me give you an example, quick one. The Cassini radar and the imaging experiments discovered lakes and seas on the surface of Titan. These beautiful images. But there was a lot of discussion about, were they really liquid, how deep were they, what were they made of? The radar system actually was able to tell us that, because instead of tilting the radar antenna to the side to make an image, it was possible to point the radar straight down and actually send signals through these large seas and some of the lakes and detect the signal from the bottom of the seas as well as the top. And so we could learn the depth, and then by determining how much the signal was attenuated or weakened by its travel, we could actually say something about the composition. So being able to follow up in that way is really extraordinary. Now, there are lots of wonderful instruments that we would all love to fly today back to the Saturn system, but there isn't enough time to tell you about them.
I think I want to add another thing. Sometimes you get serendipitous kinds of discoveries. And I think one of them for Titan that helped confirm you had liquid in those lakes and seas was actually to see a specular reflection. If you look at just the right angle for the sunlight coming down, hitting the liquid, coming back up, the visual and infrared mapping spectrometer saw a beautiful specular reflection once the sunlight reached the northern lakes and seas. So we could point to that and say, okay, that's what you see with the liquid. And then, of course, probing the depth is just a further confirmation of what the composition might be. I think if I could, for a future mission, there's so many discoveries Cassini's made to follow up on, and that's what's great about exploration. But certainly a couple of them to go back to Enceladus with the instruments, possibly to look for life, maybe to land in a lake or sea on Titan and actually sample and see what it's made of. And could you have really unusual astrobiology in a methane sea? And of course, the rings are incredibly beautiful, and maybe even for me to get closer to those rings and actually see how the particles interact and collide. I think that would be a great mission, a probe into Saturn's atmosphere to measure things like Nobel gases to depth. So many things we could do to go back. And let's not forget Uranus and Neptune. Maybe we need Cassini-like orbiters around those two worlds too.
All right, I think we have a question right here in the front row.
Hi, Morgan, I think you had a really good point that this is the first chapter of the book, and there's a next generation, and a lot of us are involved in education, and there's a next generation of young scientists and, even just kids that are in school that are looking to you and what you're accomplishing right now. And do you have something that you might want to say to them?
Should I start? Okay. Well, I think the most fun thing about working in planetary science is that there is no single path to get there. I've had some students or some kids come to me and say, okay, what should I study to come and work at NASA one day? And my answer is follow your passion, whatever that happens to be. It could be biology, it could be chemistry, geology, it could be engineering. Any of those paths is the correct path. So as long as you love what you're doing, and it happens to have something to do with space, you'll probably end up finding your way here. So that would be my advice, is pursue your passion, and then no matter whatever you end up doing, you'll be happy.
I'd just like to add to that by saying that I think that planetary science is one of the most remarkable fields to be involved in, because really it's got a place for everyone. It's got a place for chemists, biologists, physicists, unlike other areas of astronomy where you're studying stars and galaxies, and it really just takes a lot of physics. But in planetary science, there's everything there. There's geology. As we've discovered on Titan, there's a place for people who are oceanographers, which we would have never anticipated outside of the Earth. So you can really study almost any field and then wind up studying our own solar system, and I think that's great.
I would add one of the things that I told my daughters, and because I heard this from my mom as well, don't be afraid to take lots of math and science and classes that might be a little bit harder. Keep those doors open. You know, give yourself as much breadth and opportunity, because you may change your mind along the way when you go to college. And both my daughters did that. They started out one direction and went a different direction. So keep your doors open. You know, that would be my advice.
We have another question here in the front row.
This is a bit of a career-centric question, so I apologize in advance. As a concept designer in science fiction, has science fiction inspired or informed potential usable ideas for you? Ever?
That's a good question. I love to read science fiction, yeah.
Well, that's a great question. I can't think of an instance where I think science fiction has inspired a lot of us to go into this field. And it's always, it's like two sides of a coin, where we have the science that we love, and then on the other side we get entertained by the science fiction. I certainly think that science fiction has taken its inspiration from some of the discoveries that come out of science around the solar system, the Europa report and these sorts of things. But I think that just keeping an open mind and being curious really is great for both.
So I'm going to date myself. One of my inspirations was The Other Side of the Sky by Arthur C. Clarke, which was yes, I know, his eyebrows went up. He wrote it a few years before I actually read it. The thing about it was that it drew a picture of a progression of space activities and accomplishments in a very short number of pages that, as a kid, really inspired me, because when you're young, you don't get a sense of how time passes and, you know, what has to come before in terms of accomplishments. And it was drawing that kind of step-by-step story in which this first-person scientist talking about going into space, building a space station, and then at the end of the story, his son is about to leave on a trip to Mars. And it really drew the picture of that generational approach to space exploration that impressed me as a kid and still impresses me today. So read it, it's great.
Yeah, I'd say I'm a big fan of Star Trek. You know, I grew up watching the Star Trek series, and I thought, wow, wouldn't that be really cool? And that inspired me to be an explorer, because there were so many creative plots and so many creatures and places that they went that I really enjoyed Star Trek.
Yeah, the creativity in science, I think, is a critical element that people who maybe aren't going to study to be scientists tend not to realize. That this is something, when we're talking about the potential for life in a methane or ethane lake on Titan, what that might look like. Or now we're discovering so many exoplanets that, I mean, the properties there could, pretty much anything that you can imagine that still fits within the laws of physics probably exists out there in the universe somewhere. So being able to use your imagination to try to come up with as creative of a solution to some strange set of conditions that might exist in the solar system or beyond is important. It's an important part of our job. When we're asking a question, we want to make sure that we're designing the best experiment to find the answer, and the answer may be really different from what we might expect.
Well, as the good Mr. Spock would say, fascinating. Are there any other questions for our science panel here in the house? All right, I think we've got time for one more. And then Kendra, how are we doing on Ask NASA questions online? Ooh, okay. All right, we'll do one quick one and then one from social. And then any other questions that you have or that you have later, you can tweet those to @NASAJPL or @CassiniSaturn, and we will get you answers.
Hi, I'm from Johns Hopkins Center for Talented Youth, and our kids have lots and lots of questions for you. So one of them is, how would Cassini react if it was contacted by aliens? And how would this be recorded and transmitted? And was Cassini designed to handle that kind of contact, potentially?
I'm not sure Cassini was designed to really handle that.
That's a good one for the engineering panel, isn't it?
Absolutely, yeah.
Can we put that to the engineers?
Way to punt, Jonathan.
Let's hand it over to the engineers, yes.
Okay, let's go ahead and go to those social media questions. So can we get a microphone for you, Kendra?
Thank you. Gil Bryce asks, what sort of information do you hope to gather during the final plunge?
During the final plunge, we'll have 8 of our instruments on, including the ion and neutral mass spectrometer that's going to directly sample Saturn's atmosphere. So as we're going in till the very last second, we'll be getting information back about the composition and the environment around the spacecraft.
Does anyone have anything else to add?
Well, I would just add that, you know, there are some very fundamental questions about Saturn and its evolution, and some of the things that hopefully Cassini will measure during that plunge will provide some answers, like the ratio of helium to hydrogen, which we know for Jupiter and we don't know quite so well for Saturn.
I think we have time for one more social question.
I Roll with Soul asks, how far into the atmosphere is Cassini expected to survive before breakup?
Not very far at all. We have just little tiny thrusters. They're about 1/8 pound each. And if you look at, there's a half-scale model of Cassini in the auditorium here. There's one on the table. It's huge. So we think maybe about the level that the space station orbits is all before we hit atmosphere that's thick enough to turn it away, and very shortly thereafter, Cassini will disintegrate and then basically melt in Saturn's atmosphere.
All right, and with that, let's thank our science panel. Okay, you may be wondering what the heck is up with this monitor that's to my side, or what this gentleman is doing here. You're about to find out. Okay, so 83 minutes one-way light time separates us on Earth from Cassini at Saturn, and there is no chase plane. So you might be wondering, how can I see where is the spacecraft in relationship to the planet, and what is it doing right now? There's a solution for that, and it is called Eyes on the Solar System. And here to show us more about the new Cassini module is one of the people who made it, Jason Craig, technical producer. Take it away, Jason.
Thank you, Stephanie. Okay, so first I want you guys to know you can download this right now and do what I'm doing. If you have your laptop, go to eyes.nasa.gov and click on the Cassini picture, download, quick install. It takes like 40 seconds, and you're good to go, exactly like what you're going to see here. Okay, so this is a 3D real-time interactive simulation of the entire Cassini mission. And I mean the entire mission. You can watch it in real time for 20 years. I don't recommend that. But you're in charge of time, so if you want to go backwards, you want to go forwards, you can do anything you want. So let's rewind a little bit. I can go to any point in the mission. The dates are down here. There's a lot of talk about Enceladus on the stage, so let's actually go look at Enceladus for a second. So look at the bottom there, there's these fascinating geysers. We had no idea they were there. We actually had to send the mission out there and notice it. So let me light it up for you. So it's just such an incredible thing. It's just so exciting to be part of this. You can look at every single pass. I'm going to show you the Cassini car wash right now. So we actually sent Cassini through here on one of our flybys. So if you're really serious about learning about Cassini, we have every flyby represented here, including 127 Titan flybys. So have at it. I'm going to go to Enceladus, and let's go down to this one, E21, 10/28, 2015. We decided to fly right through them. Go ahead and turn on the ion and neutral mass spectrometer, which you just heard about, angled so that it's right in the plume. Want to confirm without any doubt whatsoever that this plume is made of water. So we're going to the timeline. You can see the timeline expanding, and here we are back on October 28th, 2015, where we're going to kind of shoot the plumes right here. So it's going to go right on through. So this is actually spectacular, and most people want to know, was there a risk? Was there any kind of risk whatsoever? So yes, there was a risk analysis, and it was determined that it was sufficiently small that we should go ahead and do this. And the INEMS instrument is on the corner of Cassini, and it's angled right into this stuff. So it went right through, sniffed it, tasted it, and confirmed that it was in fact water. So there is a subsurface ocean at Enceladus, and it is full of water. So you quickly want to see where Cassini is now, just right here. This is a live simulation shot. You've got the distance to Saturn here, countdown to the end of mission, and the speed. It's 17,000 miles an hour. Oh gosh, I should put this on kilometers. We don't want to cater exclusively to the American audience. So, all right, now we're in kilometers. That's better. So this is where it is now, and let's speed up time. Spoiler alert. This is 30 minutes per second. All of these rotations are accurate. You can see what Cassini does all the way in. Let's speed that up a little more. How much time do I have? All right. Okay, so here we go. Spoiler, this is what's going to happen. Now I got to slow down because spacecraft get faster as they approach And you can see the speed going way up. And this is the signal. That is the speed of light signal back to Earth, a data dump. And it takes 83 minutes to get there. So we don't really know for 83 minutes. So pointing at Earth out that way, let me show you kind of a cool perspective of this from above. So there's the final transmission right here. I want to show you just how slow the speed of light is. It's ridiculously slow, so relatively speaking. So let's pull out from let's pull right on out from Saturn. So there we are. This is real-time speed of light, and it just crossed the outer moon Iapetus. Just think about this. This is the speed of light. Now I'll show you really how slow it is. Let's go above the solar system. You can't even see the signal. That's how slow. The speed of light is going in real time right here. You can't even see it yet. So I actually have to speed up here. This is 5 minutes per second. So this TS is transmission start. Each number means that's how many minutes you have left of transmission. And now let me go back to real rate. So there we are, speed of light. It just crossed Jupiter's orbit, and it's still very far from Earth. And this is moving. This is the speed of light in real time. So it's kind of cool to see this. So 3.5-hour transmission at the end. We get it 83 minutes later. And you can watch all of this in here, along with all kinds of cool things, like the seasons of Saturn. You've probably never seen this before. This is a very, very sped up 15-year back and forth cycle of the shadows on Saturn. The ring shadows. The rings cast shadows onto the planet itself. They're gorgeous. And you see where summer becomes winter and vice versa. So the year on Saturn is about 29 plus years. It's pretty crazy to see this sped up. So every picture of Saturn, you can go back. It's all accurate when you check it. Okay, let's go back to live. And that's it. I'm getting the yank. So eyes.nasa.gov. You can do this for yourself. It's a real-time, accurate simulation. We work directly with the scientists, some of whom you've talked to. We use all the real data, the same thing the engineers use. Thanks very much, and give it a shot.
Thank you, Jason. And Jason, before you go, NASA Eyes is streaming on NASA's new Twitch channel, right?
Yes, that's right. Go to twitch.tv/NASA. It's on there right now. You can watch this view all the way in.
Thank you. All right. So you have heard about the science. You have seen the daring maneuvers that Cassini will take. Let's hear from the people who are helping to make that happen, the engineers. So please welcome to the stage our engineering panel, which is made up of Earl Mays, the Cassini project manager, Julie Webster. Come on up, guys. Come on up and join us. The Cassini spacecraft operations manager, Luis Andrade, Cassini guidance and control engineer, and Molly Bittner, Cassini systems engineer. Welcome, engineers. So just like our science panel, I had them think about some of their favorite moments from the mission, and they have some anecdotes and they have some images in their hip pockets, but we want to start with what it is that they do. So I challenge you to see if you can do this without using any TLAs, no three-letter acronyms. Yeah? Okay, it's a throwdown. All right. So we're going to start. Take it away, Earl. Why don't you tell us what is it you do on this mission?
I'm the CASPROJMGR. I'm the Cassini project manager. Before I tossed budgets and schedules around, I actually had some chops in spacecraft engineering and navigation, but now I'm just the project manager. I don't have any pictures, but I thought maybe I'd share an interesting anecdote because, if you know, in astrodynamics, we are just really prone to killing the holidays. 4th of July, Labor Day, anytime we can make the flight team work on a 3-day weekend, we do. And so for probe release, Huygens probe release, Christmas Eve. And we had a lot of Europeans in town because, of course, it was their probe and they wanted to make sure that we got rid of it properly. And so we had a whole bunch of expats in town, and we had Christmas dinner at my home. And it was just one of the nicest Christmas meals we've had. Very simple, but had just international. We had people from France, the Netherlands, England, and of course, a fair contingent of Americans as well. It was just a great day. All yours.
That's your story?
That's
You're
my
sticking
story.
to it? Okay, I'm Julie Webster. I'm the spacecraft operations manager. I first went to work for Earl when he really had chops, when he was the spacecraft operations manager. I actually started with the spacecraft in 1995, so I was there for the first power on. I was a test conductor, so I kind of orchestrated the test as we built up and went through. This is what Cassini looked like when I first saw it. So it's a 12-sided hunk of aluminum with about 10 miles of wiring inside of it. And believe it or not, I sat inside that hunk of aluminum as we would power things up, because I'm kind of I guess I engineer by touchy-feely, so I actually sat inside that as we powered things on to hear what they sounded like and what they go through. And I was telling another news crew today that when Cassini goes in, that's what I'm going to see. If I close my eyes, I'm going to see the inside of that 12-sided bay. Got another picture of it looking a little bit more professional. So this is what it looked like as we were building it up. That's a probe simulator. I think a lot of the other things were on there. We'd put the high gain antenna on. We didn't have any of the thermal blankets on yet. I think this was right before we were getting ready to go up to solar thermal vacuum. And then the next picture is, of course, it's real picture, the way it looks to everybody else today, and in all its glory, in all its glory. Earl tells me those gold thermal blankets are not as gold anymore, but I said they're pristine in my mind. So that's my part. I'm responsible for the health and safety of the spacecraft. And Molly is an ex-team member, almost ex-team member. I still got 10% of your time, and Luis works for me also. So
yeah, my name is Luis Andrade, and I'm the lead guidance and control engineer for Cassini's very final sequence of commands. And as the guidance and control engineer, pretty much my job is to determine Cassini's orientation in space, and also to steer Cassini using the onboard thrusters and reaction wheels in order to point at different targets of interest. And tomorrow, during the final plunge, I'll be in the mission control room at the front console, monitoring real-time telemetry as it comes down from the spacecraft, and I'll be calling out key attitude control events as they unfold. And for my quick anecdote, could you show my first image, please? So I've had a lot of great moments, but I'll tell you about this one. This is an image that Cassini took of Pan, and Pan is Saturn's innermost moon. And the reason that this is special to me is because it's the result of an onboard vector update that I did. And if we didn't do this vector update just right, Pan would have been completely outside of the camera's field of view and we would have missed it. And over the years, I've done a lot of these vector updates for Titan and Enceladus, but this one really stuck in my mind because I remember when these images started coming down from Cassini, the scientists were just ecstatic. They were so happy at how great these images came out. And I remember at that moment, it really hit me. You know, I have directly contributed to a scientific result of this magnitude. And as a young engineer, it was really inspirational to know that, you know, in some way, I'm contributing to Cassini's legacy, which is going to live on long after I'm gone. So can we show the next image? So we got over 50 of these Pan images, and when you stitch them all together, you get this really cool video of Cassini's encounter. This is not a simulation. This is what Cassini really saw. And that's pretty much it for me, so I'll hand it over to Molly.
All right. Hi, everyone. I'm Molly Bittner. I'm on the spacecraft operations team. I'm on Julie's team, and I am a systems engineer, which basically means that I oversee the entirety of the spacecraft. So not just one subsystem, but how they all work together. So I actually have an image, too, from 2015. So this is Enceladus's plumes that a lot of the science team has talked about. But to me, this picture represents sort of the spacecraft as an orchestra, right? So that's how I view the spacecraft, all the pieces working together to get us this beautiful goal that we have. So this was in 2015 in one of the sequences that I was lead on. And I remember designing the orbit trim maneuvers, or OTMs, if you like acronyms, leading up to this flyby. And it was a really low altitude where we just skimmed over the top of those plumes. And we had Luis's team guiding the attitude of that flyby and the navigation team. And we had all the subsystems working together. And that's really what I value on this team, is every different part works so well together, and really seeing it all come together to deliver this great science is really amazing.
All right, with that, we're going to go ahead and open it up for questions. Who's got some engineering questions? Vance, right here.
We've had this question passed off. They said we should ask the engineers, not the aliens one. I'll leave that to you. What will happen to the spacecraft as it enters the top layers of atmosphere? What changes do you predict will happen?
In terms of the spacecraft, well, the thrusters, the little thrusters, the little quarter-pound thrusters that are at each corner, they were quarter-pound to start out with. They're about 1/8 pound now because of the pressurization. They'll start fighting the atmosphere. And Luis is going to call those steps out. As we start to fight the atmosphere, we up the data rate to 1 per second so that we could get the thrusters as fast as we could. And eventually that's going to be overcome. And we'll lose the ability to point the spacecraft because it has to be pointed. These guys convinced me that they wanted to go to half milliradian. We usually bang control at 2 milliradians, but they said they could hold on to it for 1 second longer if we stayed at the half milliradian. You know, a milliradian is 1/17 of a degree. So we're pointing within 0.01 degrees, and as soon as we lose the ability to do that, it will go off, and then it'll start basically disintegrating, melting. Not really tumbling.
Well, I mean, yeah, like Julie said, we're going to be fighting as long as we can, but really, we expect to lose signal in about 1 to 2 minutes if we're lucky. We're going to lose signal, and Cassini will go on for a few more moments, but essentially after we lose the signal, we don't know its state.
But you don't expect high rates. You're not going to really be spinning like
Oh,
a
no,
top.
no.
It's going to very gradually drift off point and find a more stable aerodynamic attitude, which won't be pointing at the Earth, and a minute later it'll just be vaporized.
And the atmosphere is going to make Cassini more aerodynamic by stripping away stripping away parts and setting the attitude in a more aerodynamic fashion. Yeah.
Okay, let's go ahead and take some social media questions. Kendra, you got some Ask NASA questions for us?
Mark is asking, what improvements in Cassini were made via software over the last 20 years?
Earl. We'll start. There are a bunch. First of all, Cassini, when we launched, didn't have the capability, the software capability to do orbital operations. We had the basic structure, and we knew all the hardware worked, but all the control laws and everything, all of the algorithms to actually say, there's Enceladus, turn and point and shoot with the reaction wheels weren't on board. Those were all developed during cruise.
We couldn't dual record.
Right. We could not dual record. We knew that we had 2 recorders. We knew that all the strapping and wiring would work, but the software and smarts to do that was not there. So there was the whole baseline set of software and development that we did during the cruise. But then on top of that, the flight team took their own experiences and did some augmentations to the software in order to adapt to some of the changes and idiosyncrasies we saw in the spacecraft. I'll let you speak to those.
Well, the ATLO team and the design team actually punted to Earl's group. They said, oh, you got 7 years in cruise, you're not doing anything. You might as well rewrite flight software while you're going out there, which was a surprise to the scientists who thought we were going to do science going to Venus. So we had 3 demarcations. We had 3 main areas that we wanted to upload. So we uploaded in 2000, we uploaded in 2003, and then, as Earl said, we made some corrections in 2007. We made some major corrections to fight off a couple of the things that the solid-state power switches would occasionally trip off. They had a flip-flop circuit in there that would occasionally trip off, and it wasn't dangerous to the spacecraft, but it was annoying and it cost science, so we would stop that. Attitude control continued because they had to continue to write star fields and Cassini vectors and Saturn to Sun vector.
Yeah.
So what do you do with that? So there were 3 main revisions that were designed pre-launch. I mean, we knew that. And then there were probably 5 or 6 iterations along the way. The last time we did a full flight software was really 2010.
But the one you've missed, I think maybe the most telling, was that we realized the spacecraft, when it safes, when it gets into trouble, and it's called safing, turns off all unnecessary loads, points to the Earth, says I'm in trouble, and calls home. Well, the spacecraft was wired to do that at 5 bits per second. At a 10,000-bit transfer frame, you can imagine how long it takes us to get 1 frame of telemetry back, much less the number of frames we need to diagnose the problem. So these guys figured out pretty quickly that only in the most dramatic of safing situations do we not know where the Earth is. And so for all of those cases, they rewired fault protection so that we would use the high-gain antenna at a very high data rate to bring the diagnostic signals back, and it saved us. It really did. That 5 bits per second is just an agony. You can't imagine how slow that is. And so they rewired it so that unless attitude control was completely lost, we were in a manageable state. And I think that was one of the biggest changes.
It was. We knew very, very quickly that we just weren't going to lock up on the 5 bits. Even 10 bits at Jupiter, that's really hard to do. And, so there were a couple questions from the media yesterday about why don't you go to your low gain and get a longer signal. And that's exactly right. You hold the higher signal and you can get science data. You're getting science data to the last second. So you could stay with the low gain signal for 15 more seconds, but it takes 30 seconds for the spacecraft to reconfigure to the low gain. So you're losing all that science while you're reconfiguring to hold a maybe signal going out. It was, and we've saved twice since we built that in 2003, and both times it worked like a charm. It was the greatest thing I've ever seen when the spacecraft went off sun point, back to Earth point, and started dumping down 2,000 bits per second, and we were able to diagnose the problems very quickly.
Right, more questions here in the House? Yes, we have a very important go back, courtesy Jonathan Lunine from the science panel.
Yeah, so did you hear my question earlier?
No. But we were warned.
We were warned.
Oh, you were warned? I'm so sorry.
We have a good answer,
There's a 5-letter word.
Well, the kids are interested in alien life. They want to know, So was Cassini sort of built with that possibility in mind?
I'd say no.
No?
No, it really wasn't. I mean, Cassini was built to investigate the entire electromagnetic spectrum. It was built to do geology. It was built to do chemistry. But it really wasn't about life. It was about maybe perhaps the basis for life, in a sense, what we've seen at Enceladus. But as a life finder or something that could discern, I mean, I'm not an astrobiologist, but even asking that question, trying to find something that could give you a definitive answer is extremely difficult. And Cassini was more to just do a whole survey of the system. So say that's a long no.
Great, thank you.
Okay.
And we didn't carry a golden record for the Star Trek team to pick up either.
We do have a DVD, though.
We do have a DVD.
Yeah, I think we've got one more question here in the front row in the House.
It's more of a comment than a question. In Hollywood, it's offensive to name drop, but I'm going to do it right now. I've been very fortunate to work with some big name directors, James Cameron, J.J. Abrams, Steven Spielberg. That's the name dropping part, and I apologize. But I say that because I'll dare to speak for them as well, because I've spoken enough to them, that you guys are the true inspiration and the real stars here. It's such an absolute privilege to be amongst you and your minds. I just want to crawl inside every one of your skulls and just dance around, because it's so fantastic to experience what you're sharing with us. So thank you.
Well, Molly, you and Luis should tell what inspired you. I kind of was looking for a job when I found this one.
Sorry, really quick before to answer your comment there. Actually, last week I was at Long Beach Comic Con, and I did a talk there, and it's a sci-fi convention, and those people were great. They love science fiction, and they loved hearing about real science, space missions like Cassini, and they go very well hand in hand, so, yeah.
Yeah, I'm with that. I grew up watching Star Wars, of course, and playing with Legos and playing with all the alien-themed Legos, so there's my alien pun for you. But I just love space in general, you know, so anything that's space-themed, I'm a huge gamer in my spare time, and so anything that has space involved, I love. And then I get to come to work and inspire people. And the past couple of days of talking to the media has just been such a privilege, right? So usually I'm working with all these great team members, and it's amazing, but to be able to be inspired by you guys, too, because sometimes we get wrapped up in our everyday office, you know, normal work that we do, but having you guys come here and say that you're inspired by us, that really helps us go forward.
One of the best things that ever happened to me was on a different spacecraft. We'd had a lot of problems on an earlier mission that I worked, a lot of problems, and we were all stressed out. We were working 12 on, 12 off. I didn't like them, they didn't like me. And, you know, we were all just, go away, I need sleep. And the project manager at the time wrote us a letter thanking us for saving the mission, and that what we did was a miracle to the average person on the street. And I have never forgotten that, never. And gone back to, oh yeah, and I like these people too, once I got a few hours sleep.
Yeah, just to comment again, we had an open house here a few years ago that was overwhelmingly crowded, overwhelmingly hot. People were parking on the freeways and traipsing across the Arroyo to come on, and just reminded us again of how blessed and lucky we are. I mean, I'm walking down the road and it's hot and and I hear from the back of some of you say, what's it like having the best job in the world? You know, oh boy, he's right. I do. It's really cool. And so thank you. So we're very lucky.
And with that, let's thank our engineering panel. Okay, so on social media, it's pics or it didn't happen. And thanks to Cassini, we've got lots of pics. This spacecraft has taken nearly 500,000 of them. And here to tell us more about the awesome images, the last images that we're expecting to be coming down just hours from now from the spacecraft, we've got one of the people who put together the sequence that will take those photos. So as our engineers leave the stage, we're going to welcome to it Mike Evans, ISS team associate from Cornell University. So come on up, Mike.
Right, thank you. Well, as I've been introduced, I don't have to say who I am and what I do. I suppose I should just quickly say, you know, what I do on Cassini. I led one of the teams that actually allocated time to actually do the science. And that was, you know, not really part of my imaging job. And then for my imaging job, I'd identify opportunities, I'd put requests in, you know, please let us do this, and then I'd argue for them in the groups that actually allocate the time. And once we actually get, you know, succeed, I do all the paperwork. Well, it's not actually paperwork; it's all done, you know, online with files. But I make sure that all the I's are crossed, or all the I's are dotted, all the T's are crossed, and then I actually help build the pointing design, which is where to point the spacecraft when, and in many cases I actually will build the camera commands, you know, open the shutter at this time, keep it open for 37 milliseconds, use this filter, use that filter, and then in many cases when the data comes down, I actually am able to, I'm involved in the analysis of the actual imaging data. And actually, if you could bring up my first slide.
Absolutely.
Let's see. Okay, so the other people who've been up on stage today have told you know that either their anecdotes or their favorite images. Well, this is both my favorite image and the anecdotes that I'm actually going to tell you. This is the small moon Daphnis that orbits right at the edge of the A-ring of Saturn. It's only about 8 or 9 kilometers across. And it sits in this gap called the Keeler Gap, which radially is only about 40 kilometers across. And it's not there by accident. The gap is there because the moon is there. The moon's gravity actually, you know, clears the gap. And if you look just to the bottom left of the moon, you can see a little wisp of material. And I'm not talking about the edge waves, I'm talking about the wisp of material. That's all due to the interaction between the gravity of this moon and the little ring particles that are actually just, you know, part of the ring just outside the gap. And my anecdote is this moon misbehaves. It apparently, you know, when we look at its orbit, you know, it apparently, we don't know why yet, but it apparently jumps forward a little bit and jumps back a little bit in its orbit. But it has the nerve to do it when we're not looking. So when we're down equatorial, and you know, the rings are edge onto us and we can't see this moon, something has happened on the last two equatorial periods. Something's happened to this moon, and it's jumped a little bit forwards in its orbit, or in one case it may have jumped a little bit back. And the problem with that is we have to be very close to get these high-resolution images. And if it's not exactly where we think it is, if it's not exactly where we tell the cameras to point, we miss it completely. We don't get any images at all. And that's what happened to the first observation we had about 2 years ago at Christmas. We missed this completely because the moon had actually jumped, and we were pointing where we thought it was, not where it actually was. So when this happened back in January of this year, we knew, well, it's a danger. So let's hedge our bets. Instead of just pointing where we think it's going to be, let's, at least for these closest approach images, let's actually do a mosaic. Let's point, you know, one frame slightly ahead, one frame a little bit, you know, further ahead, where we think it is, one frame behind, and one frame a little further behind. And as it turns out, this image is from the very first frame. It's as far away, if it had been any further away from where we thought it was, we would have missed it completely. So we actually only have images from this one footprint. So we took, I think, it was somewhere between 50 and 60 images on the way in, as the resolution increased, but we only got it in 3, and all 3 images were pointed at exactly the same points. So even with all the care that we'd taken, we almost missed it. But the images that we did get were incredible. I mean, I tell people, you know, I look at this and I think it's some sort of Art Deco object. It's the hood of a car. It's, you know, it's something. It's clearly not the flying saucer shape that Pan has, that Luis was talking about earlier. And then if you could go on and show the next image. This is just an example of my bread and butter work. I mean, this is, you know, the edge of the A-ring. There's the F-ring, you know, the thin narrow strip, and 2 moons, the so-called shepherd moons either side of it, Prometheus inside, Pandora outside. And the sort of thing I do with this image is I do astrometry. So basically I figure out where all the stars are in the image, make little corrections so we know exactly where the camera was pointed. Because even though we tell the camera points in this direction, it never actually points exactly in that direction. It's usually somewhere between, it's usually about 20 arc seconds off. And those 20 arc seconds are something like 15 or 20 pixels, and that makes a big difference when you're trying to figure out orbits. So I would, you know, figure out where we were pointed, then, right, the moon is in this position, and that corresponds to this direction, and then that data gets sent off to people at JPL, and they put it all together into numerical simulations, and then update what we call the ephemerides, which is basically the orbits, the positions and times of all the objects actually in the system. And then if you could show the final image.
We've got about 30 seconds.
Okay. No more final image. So do you want to take questions?
Okay, so because we are looking forward to those final images, we wanted to let you know where and when to look for them. We anticipate the data on the ground and on the web around 8 o'clock Pacific, 11 Eastern tonight. Just go to go.nasa.gov/CassiniRaw. Again, that's go.nasa.gov/CassiniRaw. And a big thank you to Mike. And thank you to all of you joining us here in the house and online. We hope that you'll be back with us as we broadcast live from Mission Control here at JPL as the final data are received from the spacecraft, the epic end of Cassini's grand finale. Get your coffee. We're going live at 4 a.m. Pacific, 7 a.m. Eastern, 11 o'clock UTC, so Europe gets a break. You can watch on NASA TV or nasa.gov/live. Thank you so much for being here today, and we'll see you online.